And I wanted to do just a real quick recap. Um, and all I'm going to do, I won't even share my tablet. I just have our notes up here. Um, so the things that I wanted to recap is just kind of like the key Hamiltonians that we developed yesterday. One is the P.A Hamiltonian, and sort of the final form that we worked it into was um, we had this, let's make this a little bit bigger. Our matter Hamiltonian, which was a harmonic oscillator, our cavity Hamiltonian, which was a harmonic oscillator. Then we had this bilinear coupling term, which really involves the momentum operator of the matter subsystem uh, dotted into the vector potential of the cavity subsystem. And the matter subsystem has these A dagger and A operators. The cavity subsystem has these B dagger and B operators. And then we had a third term. So this was a linear term in each subsystem. And we had a third term, fourth term, which is quadratic. It's got basically the square of the vector potential operator for the cavity subsystem. And that's the so-called P.A Hamiltonian, or the minimal coupling Hamiltonian. And we went through this PZW transformation, which ultimately got us to this second Hamiltonian, which is called the dipole gauge Hamiltonian, or the D.E Hamiltonian. And the final form here is you've got a matter term, which is a harmonic oscillator, a cavity term, which is a harmonic oscillator, a different bilinear coupling term, which has really got the dipole operator of the matter dotted into the electric field operator of the cavity. So things have switched. Now you've got B dagger minus B and an imaginary unit, because that is the electric field operator for the cavity. And you've got an A dagger plus A, which is related to the position operator of the matter, because I've really the dipole operator is just position times charge for the matter subsystem. And then I've got this thing called a dipole self-energy, which is really the electric field operator. I'm sorry, the dipole operator for the matter subsystem squared, and it's got a magnitude of the electric field, but no cavity operators on it. Actually, in our notebook, so we did not get this far. In our notebook that we're going to implement today, we're actually going to use a different Hamiltonian than the D.E, and it results from one additional unitary transformation, which is of this form. And basically, this is a very interesting unitary transformation, and I wish we had much more time so we could talk about it more. But it's a very funny transformation that actually doesn't, if you work out the commutators, they do not terminate. They go on forever, but it's a convergent series, and it ends up having the effect that when you apply this operator to the cavity raising and lowering operators, they pick up factors of I and minus I. And sort of the net effect of applying this phase transformation operator is to switch. Now this bilinear coupling term really only impacts the bilinear coupling term into one which now looks like this. So it gets rid of the imaginary unit in the bilinear coupling term, but also ends up changing things around so that now you're back to the vector potential operator for the cavity subsystem dotted into the dipole operator of the matter subsystem. So that's the real difference between the D.E Hamiltonian that we got to yesterday and the so-called Pauli-Fierz Hamiltonian that we're actually going to implement today. So I did want to at least take a minute to remark that because when we get to the notebook, you're going to see this Pauli-Fierz Hamiltonian is one of the things that we do, and we won't actually implement the D.E Hamiltonian, but it's just one more unitary transformation beyond it. And then the other thing that I hoped we'd have time for, but we didn't, but I think in our the document that we linked to, there's some videos on tensor products. So I'll just give them really short shrift here, and I would encourage you to watch those videos if you want to learn a little bit more about the mechanics of these. But basically, what we're going to do is we're really going to build a matrix representation of these Hamiltonian operators and some basis. And that basis is basically going to be a tensor product basis between the energy eigenstates of the bare matter Hamiltonian, which are the harmonic oscillator states, and the bare cavity Hamiltonian, which are also harmonic oscillator states. So we'll denote those basis states like this. We won't actually even really need to think about them in the notebook, but that this is the basis. We'll denote it with N comma M, where N denotes the quantum state of the matter subsystem, and M denotes the quantum number of the cavity subsystem. And really our basis states, you can think of them as a tensor product. And this is just a little note about how you actually compute a tensor product. We'll be using a Python library, a NumPy library called cron, or NumPy method called cron, which is going to take the Kronecker product, which is just a tensor product. But what we'll sort of do more explicitly is to build the matrix representation in this tensor product basis. We're really going to think about taking tensor products of sort of our submatrices. So we'll build like a submatrix just in the basis of matter states, and then we'll take a tensor product into an identity matrix, where that identity matrix will sort of span the state space of the photon subsystem. Then we'll do the kind of complementary thing for the cavity subsystem. We'll have an identity which spans the state space of the matter, and we'll take the Kronecker product with a Hamiltonian that we've built just for the cavity subsystem. And then we'll have, for example, the interaction Hamiltonian is naturally going to be in the tensor product space of both the matter and the cavity subsystem. So that's how we're going to represent things today. So, and then there is one other thing. Okay, so I don't want to linger too much, but one other thing. Someone asked a question yesterday about the momentum and position operator for the photon, and I was like deer in headlights about it. But actually, it's quite simple. So yeah, absolutely. The photon does carry momentum. The photon, occupies a region in space. So you can think about the momentum operator as telling you about the momentum that the photon carries, which is going to be related to its frequency. And similarly, the position is, the photon occupies some position in the cavity, so you can use the position operator to tell you about that. And again, if you took expectation values of any particular cavity state, so like the ground state, the expectation value of photon of momentum would be 0, because it's sort of like equal amounts of right and left traveling photon waves, because it's a standing wave. And then the position expectation value would be 0, because the particle is most probably found in the middle of the box. But it has uncertainty, so it spreads. And the momentum also has uncertainty, and it spreads. And actually, all the same things that you get from the harmonic oscillator would be true. So if you've ever worked out uncertainty in position and momentum for harmonic oscillator ground state, and you've done like this demonstration that it's a maximum uncertainty state, minimum uncertainty state, all those things would hold for the ground state of the cavity. Okay, so that's it. That's my really quick recap of yesterday. And I will also just see if anybody has any other lingering questions before we get into the programming part of today. Okay, so we'll get into the programming part. Really quick logistics. So we're going to go into rotation. I'll do about the first, roughly 25 to 30% of the notebook. Then Ruby is going to take over and do the next, roughly 35% of the notebook. And then Peyton is going to go third. Oh, tell Joe I said hi. Oh, that was direct message, sorry. And then Peyton will do the last third of the note, 35 to 40% of the notebook. And so we'll go in this rotation. And we'll be screen sharing, and those that are not doing the live coding, so while I'm live coding, Ruby and Peyton will be needing to type along, but they'll try to watch the chat. Once I hand it off, I'll spend my time really watching the chat in case there's any questions. So that's sort of how the logistics are going to work. And let me share my screen one more time. So here's what I'm going to do now. As I mentioned, I'm going to be using the ChemCompute server. And so I've logged into ChemCompute, and I'm going to clone the GitHub repository that we provided to you. So let me just go to my email and find where I sent everybody a GitHub repository. So in the ChemCompute server, I can go to clone a GitHub repo. So that was in Jupyter, clone a GitHub repo to your notebook. And in this place, all I have to do is just click or paste my URL and hit clone repo, and hopefully this will work. Okay, great. And then if I've cloned this repo, and it's just going to populate my main screen. And now what I'm going to do is click on the notebook to open it. All right. And what you can see is, some of the text about what we're going to do, and I'll read a little bit of this text, but for the most part, I'll just try to focus on demonstrating the notebook. I'll assume everybody's familiar with Jupyter notebooks. They're quite intuitive, but if you've never seen them before, really quickly, there's text blocks. And then there's code blocks. To execute a code block, you have a few different options. You can put your cursor on the code block and hit run, or you can make sure your cursor's on the code block and hit shift enter. Those are two ways to run. And this notebook is set up so that the content is sort of explained in text, and then there's areas that we're going to fill in below it. So, so the first thing that we're going to do, basically all of the operators in this, all of the sort of subterms of these Hamiltonian operators involve the ladder operators. And so our goal is ultimately to build a matrix representation of these operators. And so in order to do that, we're actually going to first build a matrix representation of the ladder operators. Okay. And so this takes us right down to the first function here that we're going to complete. And what you can see is the documentation up here suggests that we're going to complete this function called build ladder operator matrix. And it's going to take one argument, which is the dimension. And basically, this is how we're going to specify how many different states we want in our basis. And so if we have some time at the end, we can kind of explore the impact of growing the size of our basis. But if you've ever done any kinds of numerical quantum mechanics before, you've ultimately probably made some selection of basis. So if it's quantum chemistry calculation, you've picked a basis set, which is like an orbital basis. If you've done, for example, an active space configuration interaction calculation, you picked an active space, which is choosing the size of your mini electron basis to some extent. If you've ever built and diagonalized a matrix for a simple model problem, you've probably picked a basis and stuff like that. So this is an important numerical consideration. And essentially, the more basis states we can include, the sort of better chance we have at getting accurate energies at the end of the day. So this dimension will help us grow the size of our basis. Also, a real quick note about how these functions are set up. So I have doc strings here, and the doc strings are going to spell out basically the arguments that we pass to the function, and then the things that the items that the function returns, which could be a number or a matrix or a vector, or it could be multiple matrices or vectors in this case. And then also an example of how you could call this matrix and what the expected output would be. And so, so here's the idea that at the end of the day, we want this function to function such that if we call build ladder operator matrices, comma 3, I'm sorry, open parentheses 3, it would return two vectors, a dagger and a, or something that we could capture in the vectors matrices a dagger and a. And if we then subsequently printed a, it would look like this. This is the matrix representation of the lowering operator with 3 basis states. And if we printed a dagger, it would look like this. This is the matrix representation of the raising operator and the basis of 3 states. Okay. So that's how this function should work. And so let's work on it together. And there's comments here that are going to help us out. So, so the first thing I'm going to do is I'm going to follow this comment here, which says to initialize the lowering operator as a dim by dim array of zeros. So what I'm going to do then is I'm going to say a, which is the name I'm going to use for the lowering actually, sorry, I'm going to call it lower mat, just following this docstring suggestion. So I want the lowering operator matrix, which I'm going to call lower mat. And I'm going to set this equal to np.zeros, 3, np.zeros 3 by 3. Right, so this should create a, not 3 by 3, dim by dim. And I'm going to use dimension by dimension because the name of the input argument is actually dimension, even though my comment says dim by dim. Okay, so this is just going to create an array of zeros, and it will be whatever the input argument dimension is by dimension. Okay, and now what I want to do is I want to loop through the elements of this array and store these upper triangle elements, I and I plus 1, to be equal to the square root of I plus 1, because that's essentially the recipe for filling out the matrix elements of this lowering operator. So I need to loop over I in range of dimension. Actually, I think I need to do this in range of dimension -1. And what I'll then do is set lower mat I plus 1 to be equal to the square root of I plus 1, where I'm going to use np square root to get the square root. So this loop should basically fill out lower mat with this logic. So that's basically the upper triangle elements, I and I plus 1, are equal to the square root of I plus 1. And then I could do a similar loop to build the raising operator, right? And except for I would be trying to fill out the lower triangle elements. But an alternative way, and perhaps easier way to think about it, is to recall that the lowering and raising operators are the adjoints of each other. So the other thing I could do is actually just take the adjoint of the lowering matrix and store it to a new matrix, which I'm going to call raise mat for the raising operator. So let's do that. So in this line here, I'm going to say raise mat is equal to lower mat dot conj dot t. And then that should be everything I need. And I just want to return them here. So I want to replace that comment with a return statement. So I'll say return raise mat, comma, lower mat. Right, and so now let's make sure this looks as I expect it to, where the function returns 2 different things. The first thing it returns is a dagger, or is the raising operator. The second thing it returns is the lowering operator. And that's the order that I have these: raise mat, lower mat. Okay, so let's do this. Let's hit Shift Enter to save that code here. So now we have a function that in principle should build the ladder operators. And since I have this example here, what I'm actually going to do is I'm going to basically run this example. Okay, so let me literally just copy and paste this example below. And then below this, I'm going to say print a DAG. So I'm going to print a string first that says print a dagger, and then I'll print the variable a dag, and then I'll have a string that says print a, and then I'll have a print statement that just prints the variable a. And I'm going to run this, and I see that in fact a dagger looks like exactly like this matrix, and a looks exactly like this matrix. Okay. Now, I would also, I guess at this point, like to confirm, actually, let's see what's happening next. So yeah, let's actually just go down to the next block here, because this next block is actually going to run that function as well, with some print statements already built into it. So everything I just did up here is kind of redundant. We're going to do it with this pre-written block here. So go ahead and run that pre-written block, and you can see slightly larger matrices. So now we've included 4 states instead of 3 states. Okay. So before we move on, I think I want to just demonstrate a couple of properties of these matrices. And so, this is not really scripted into the notebook itself, but you're free to follow along if you'd like, or you can also just watch. But one of the things that I want to do is I want to take the commutator of B and B dagger. And this work exactly the same way with A and A dagger, of course. And so to do the commutator, basically what I'm going to do, so I'll say I want to do B, B dagger, right? And this is a commutation relation that we went through yesterday in the notes. And we know that the commutator of B and B dagger as operators should give me the number 1. So as matrices, if I built the matrix representation, then I should get sort of the matrix version of 1. And does anybody know what the matrix version of 1 is? Yes, the identity. Perfect. All right. Now, the real gag here is when I do this, right? So let's say com B dag is equal to B, and I want to take the matrix product with B dag. So I'm going to use the @ symbol, and I'll subtract this from the matrix product of B dag with B. So I'll do matrix product of B on the left side and B dagger on the right side minus B dagger on the left side, B on the right side. And I'll save that to com_B_B dag. And then I'm going to print okay. And so what I get something that looks almost like the identity, except for the very last element is wrong. And this will persist. This will persist as you make your B's and B daggers larger and larger and larger. You will notice that most of the matrix looks like the identity, but there is always one element wrong. So there's actually, so this is, we're by no means the first to ever observe this. This is sort of well-known fact that when we have commutation relations for operators, and then we build matrix representations of those operators on a finite basis, we do not recover the exact commutation relations. So the same thing would actually happen if we were to build our matrix representations of the momentum and position operator and take commutators. We wouldn't get I H bar exactly. We would get I H bar for some identity part, partial identity, and then somewhere in the end there would be a mistake. So there will be consequences of these inexact commutation relations as we move along, but I did want to point that out. Second thing I wanted to point out very quickly is I can make a representation of any of my cavity occupation states. So I'm going to make of the zero ket. So I'll say ket 0 is equal to np dot array, and I want my kets to basically be column vectors. So I'm going to make a column vector that looks like the following. Okay, so this is a representation of the zero ket in this basis of 4 cavity states. So what does this mean? This means that this is sort of a weight on my different basis states: basis state 0, basis state 1, basis state 2, basis state 3, right? So basis state 0 has weight 1, basis state 1 has weight 0, basis state 2 has weight 0, basis state 3 has weight 0. Okay, so this is the zero ket for the cavity. And now what I want to do is I want to see what happens if I take the action of the raising operator on the zero ket, right? So I'm going to say new ket is equal to b dagger at ket 0, and I'll print new ket. And what I should see is that, in fact, the new ket, right, is 0, 1, 0, 0. So what has happened, right, is now I have shifted to the 1 ket, right? So this is the relationship that I was expecting. B dagger on 0 ket gives me 1 ket. And if I continue, right, I can take one more just to confirm that this is working correctly. So I'll say new ket is equal to b dag at new ket, and this should in fact give me square root of 2 times the ket 2. Yeah, so this is now giving me ket 2 times square root of 2, and I could keep going, right? Well, I'll run into problems if I exceed my basis. So if I did this 2 more times, right, I've run into trouble because I try to raise into a basis state that I don't have. And also I can show you that if I try to lower from the 0 ket, I'll get 0. So that's maybe the last thing I'll do, and then we'll move on. So I'll say try ket is equal to b at ket 0, print try. And this is the last thing, try all zeros, right? What happened? I tried to lower the 0 ket, and you can't lower the 0 ket. So we just get an array of zeros. Okay. All right. So I saw a chat come in. I just want to take a quick glance at the chat, see if there's any unanswered questions. Okay, no unanswered questions. Great. Okay, so everybody feel okay with that? Awesome. So, so now that we have B daggers and Bs, the very last thing that I'm going to do before I turn it over to Ruby is I'm just going to take you through setting up the parameters of the harmonic oscillator for HF. And so as we wrote down yesterday, right, we've got the harmonic oscillator Hamiltonian. I've got momentum operator squared over 2 times mu, where mu is the reduced mass, plus 1/2 kx squared, where k is the force constant. Okay. And these are 2 equivalent ways of writing the potential, 1/2 kx squared or 1/2 mu omega squared x squared. So so we need values for k and for mu. And so I have we're going to do everything in atomic units in this notebook. So that's, my favorite unit system. Maybe some of you share my affinity for the atomic unit system. It's quite convenient for many things. It's not that convenient for atomic masses, though. So the atomic mass of fluorine and the mass of fluorine in atomic units is 34,616. The mass of hydrogen in atomic units is 1,837. So those aren't quite convenient. So remember the atomic units, this is the unit system where the electron mass has magnitude 1. So that means the proton mass has magnitude roughly 1,800. But anyway, these are the values, so we'll use those values. The force constant of HF in atomic units is about 0.6377. So where we got this is we ran a couple cluster singles, doubles, and perturbative triples calculation in a correlation consistent polarized valence triple zeta basis set. So we tried to do a pretty reasonable calculation on HF and just get the equilibrium geometry and the second derivative of the energy at that equilibrium geometry to get the force constant. And this is the number we came up with. So this is also in atomic units. And then the equilibrium bond length, also in atomic units, is this number, 1.73 atomic units. So the conversion to angstroms, you'd want to multiply that by like 0.529-ish, and you'd get the number in angstroms. And then this effective charge, right? So we also computed the dipole moment of HF at equilibrium. So it has some dipole moment that I didn't write down here. And we just divided that dipole moment by the equilibrium bond length. The dipole moment in atomic units divided by the equilibrium bond length is now the charge, the effective charge in atomic units. And with all of this stuff, right, with the reduced mass and the force constant, we have everything we need to compute the fundamental frequency of HF within the harmonic approximation. And that fundamental frequency also in atomic units is 0.01911. So we're going to go ahead and also use that number for the cavity frequency too, because the idea is we want the cavity frequency to match the fundamental frequency of HF. So that's all of these values in this table. All right. And so all we're going to do here now is we're just going to add some lines which are going to assign these values to different variables that we'll use later on in the notebook. So, so I'm suggesting the names here so that when those variables are called on later in some of those code lines that may be written for you or code lines that we'll write later, that we have maximum likelihood that those variables will be assigned to the right values. So I would recommend you use the variable names that I'm using. Okay, so I'm going to define the force constant in atomic units for HF. And again, I'm just going to take this number here from the table, so 0.6377. You should be able to copy it and paste it. And then I'm going to take the mass of fluorine in atomic units next. I'm going to take that number from up here. So m, lowercase m, uppercase f underscore AU is equal to this. And I'll grab the mass of hydrogen in atomic units, and I'll insert that here. So lowercase m, uppercase h underscore AU is equal to this number. And then I actually need to compute the reduced mass. So I'll say mu underscore AU is equal to mf underscore AU times mh underscore AU divided by the sum of mf underscore AU plus mh underscore AU. And then finally, I need to compute, well, I'm going to compute the frequency, the fundamental frequency of HF here. So omega underscore AU is equal. So here I'm going to use the relationship that we've discussed a few times at this point, hopefully well known to everybody, that the fundamental frequency is equal to the force constant divided by the reduced mass. And here I just want to make sure I use the right variable name. So K underscore AU for the force constant divided by mu underscore AU for the reduced mass. All right. And then I'm going to set the cavity frequency equal to the fundamental frequency. And lastly, I'm going to assign the effective charge, which I have up here. Z underscore AU is this. Okay. All right. And then this in atomic units, reduced Planck's constant has magnitude 1. So this is just here. Oh no. This is not arbitrary units. This is atomic units. I don't know why that's there. Okay. So let's run this. We should just get a little printout that the cavity frequency in atomic units is this number. So if everybody is good up to this point, if you could just go down to your reactions and put up a green check mark, as I'm about to do. And if something has gone wrong, if you want to go to your reactions and put up a red X mark, as I have just done. Okay. Cool. So I'm seeing only one red X, and that's from me. So it looks good. Okay. All right. So, oh, I lied. There's one more cell. One more cell that I'll do. Okay. So next thing that we're going to do is we're going to set up a function which is going to generate the potential and compute the energy eigenvalues of the harmonic oscillator. And this will, once we complete these functions, we'll run this cell, and the cell is going to call those functions using the parameters that we just defined, and it's going to actually create a plot of the potential and the energy eigenvalues. And so that'll give us like a little visualization of the energy eigenvalues of the bare matter system. And then we're going to recreate that plot at the very end once we've introduced the coupling, and we're going to see how the states are affected by the coupling. So we kind of get a little before and after coupling plot here. Okay, so let's go up to the top of this new cell then, where we have a function called potential. And the potential is going to use this particular form of the potential where you were going to pass it the reduced mass mu and omega, the frequency and then also a position, an array of position values. So we're going to actually just have we're going to expect that we can pass it a single value of position or perhaps a whole list of position values in some variable or array called x. And it'll evaluate the potential at one or more values of x using this formula. Okay, so let's come down to this function, and you can see that here are the input arguments, right? Input argument 1 is omega, it's a float, and that's the fundamental frequency. Input argument 2 is mu, it's a float, that's the reduced mass. And then input argument 3 is x, and that is either a float or an array of floats, and that's basically the position values. And then this thing is going to return the potential according to this formula. Okay, so we'll just come down here to this comment, insert code to compute v sub x here, and we'll say v underscore x is equal to the number 1/2 times the input argument mu times the input argument omega squared times the input argument x squared. So 1/2 mu omega squared x squared. Okay, and then lastly, I'll just return the underscore x. And that should be it. And okay, so that's the potential. And this function is called energy, and it's going to compute the energy eigenvalue of the harmonic oscillator for some given quantum state. And as input arguments, it's going to get omega, the fundamental frequency. So omega is a float, and then it's also going to get n, which is an int, and that will be the quantum number. And so what it's going to return is E sub n, which is also a float, and that's going to be the energy eigenvalue of quantum state n according to this expression, h bar times omega times n plus 1/2. And we've already assigned h bar equal to 1 somewhere before, but I should do no harm to reassign it here inside the function. So there it is. And yeah, we'll just say E sub n is equal to h bar times omega times n plus 1/2. And that's the expression. And we'll say return E sub n. And that will return the energy. Okay. And the final function has already been written for us. I'll just tell you really quickly what this is. So what we want to do basically just for aesthetics, when we make this plot, we're going to plot the potential, and then we're going to plot the energy eigenvalues on top of that potential. And aesthetically, it's just quite pleasing if the horizontal lines for the energy eigenvalues like start and end at the potential. And then don't spread out beyond the potential. So it's actually needed to know where does the potential intersect the total energy, and that's called the turning points or the classical turning points. And so you can find these classical turning points, quite easily. It's just basically where 1/2 k times some value of x squared is equal to the total energy for a given state. And so this is just going to find those turning points and return them. So that's already done for us. Okay. And so the remaining part of the cell, right, is actually just going to set up an array of x values. So we're going to have like 1,000 x values between minus 0.5 and 0.5 atomic units. And the 0, the center of this, will be where the equilibrium bond length is. And then V is going to be the potential. So we'll feed it omega and mu and the array of x values, and that's going to return a list of potential values for each of these x values. And we'll plot the potential, and then we'll go through a few, in this case, it's going to be 3 different energy eigenstates to just find the turning points and plot those little lines. And that'll be it. So let's go ahead and run this. And once again, what I'll ask you to do Just put up a green check mark if everything's working and you've got a plot like this. And if you don't have a plot like this, if something's not working, put up a red X. Okay. All right. So I see a couple of green check marks. I see no X's. If you still just need a bit more time, put up a red X. Okay. Well, I think we're probably good to go. So what I'm going to do now is I'm going to turn it over to Ruby. So let me stop sharing my screen. And I'm going to just monitor the chat and try not to interrupt too much. So Ruby.
Hi everyone. Hi Jay. Am I audible?
Yes.
Okay. So now if I go in the top of the notebook, then we have basically the goal is to form these two Hamiltonians. So the first one is P dot A Hamiltonian, and to form this Hamiltonian, we need a matter term, a cavity term, a diamagnetic Hamiltonian term, and then an interaction term. Similarly, if we want to build the PF Hamiltonian, then we need the matter Hamiltonian term, the cavity Hamiltonian term, the dipole self-energy term, and the interaction term. So what I will do, I will try to form this P dot A Hamiltonian. For that, first we will build a function to build this matter Hamiltonian, bare matter Hamiltonian term. And let me go back to the term. So this is how we have defined the matter Hamiltonian term. So for this one, what we need is Planck's constant, fundamental frequency, and then we need the A dagger A operators and a identity matrix. So here we will write a function to compute the matter Hamiltonian term, and we'll name it compute matter energy matrix, and the parameters will be matter dimension, force constant, and reduced mass. Now here, first what do we need? We need to call this the function to form the A dagger and A. So let's first call that function, and we will store them as A underscore. So basically these variables, A dagger, comma, A, and this is the function which we want to call, and the dimension which we'll give is matter dim, because we are building these ladder operators for matter subspace. Now what else do we need? We need this fundamental frequency, and we will compute it and save it in this variable named omega f. We'll call a numpy function square root, and so it's k divided by mu. Now we will just put these values into this equation to compute the matter Hamiltonian term. So we will save our matter Hamiltonian in matter Hamiltonian, matter underscore Hamiltonian. And simply, so we need h bar into omega f a underscore dagger comma a, and then we'll simply add our identity matrix, which we will build with the help of a numpy function called I, and simply give the matter dim, and then we will return our matter Hamiltonian. And if we'll try to run it, it should run. So mine is running. You can give a red sticky if yours is not running, and somebody will reach out to you. Now, next, what else we need to build the P dot A Hamiltonian? Next, we need bare cavity Hamiltonian term, and which we can define as h bar, frequency of the cavity, and then big dagger b plus half of the identity matrix. So for that, we will define a function compute cavity energy matrix, and we'll give parameters cavity dim and omega cavity, because these are the two things which
Oh,
yeah
Ruby,
yes, yeah.
Rajanya just made a very good comment or made a good observation.
uh,
Uh, Rajanya believes that there's a factor of 1/2 missing in your identity.
oh, sorry, yeah.
Great, thank you. Good catch.
Thank you, Rajan. Yeah, thank you. So now for this we need b dagger and b. Again, we'll call the same function. Save the b dagger and b in these variables, and then simply put these values in this equation. And I would like you to try this. I will give you 5 minutes to try this, and then I will go through it. So I will just should I turn off my screen share, or just like keep it this way, and I can just
Yeah, you can just stop sharing. I guess that's fine.
okay.
Yeah.
Okay. So I'm starting a timer for 5 minutes, and I will start writing this code again after 5 minutes, and you can try until then. And if you have any problem, please give a red mark so that we can reach out to you. If everybody is done, then they can just like type done in the chat and I can continue. We don't need to wait for like exactly 5 minutes. Yeah, we still have 40 seconds. Okay, let's go and write it down. So we have oh, okay. So we have big dagger b equals to, we'll call this function, and this time we will give the dimension of our cavity, and that's it for this one. Next we need to put all these values in this equation to compute the cavity term, and we'll save it as cavity underscore Hamiltonian so we have h bar into omega underscore cav into p dagger p, and now we need to add our identity matrix, which is np dot eye and dimension of our cavity, and it should run. Okay, is everyone's running? You can just put that sticky if it's not working for you. Okay. Now, in order to build the P dot A Hamiltonian, next we need the diatomic term, Hamiltonian. And this is the equation for that. So we have Z square, which is our effective charge, divided by mu into reduced mass, A naught square, which is our vector potential, and then big dagger plus P whole square root. For this one, we will define the function compute diamagnetic matrix P dot A, and our input parameters will be the dimension of cavity, effective charge, vector potential, and reduced mass. So let's first call the ladder operator function so that we can have B dagger and B. And we will give the dimension of the cavity. Next, we need to compute the prefactor. So first we will compute this prefactor, which we store as fac. pack is equals to, so we have z square into our vector potential, which is a naught, and this is also squared, divided by 2 into reduced mass, which is mu, and that would be our prefactor. Now for this equation we need to add the b dagger and b, and that's what we'll do in the next line of the code. So we will simply add b dagger and b and store it as b underscore sum. So we have b dagger plus b. Now we will simply, because we need the square of this sum of b dagger and b. So in this next line of code, we will simply sum it and store it in b underscore sum squared. And will be sum into, sorry, at the rate b underscore sum. And that now we will simply put all these terms into this equation and calculate our diamagnetic term. So we will store diamagnetic term as dimag dimag underscore Hamiltonian is equals to, so we will multiply with our prefactor, which is stored as fac into our matrices. So simply with this one, and I think this should work. Okay, we need to add a multiplication sign. Okay, yeah, and it's running. So I want to pause and like see if you guys are done with it, or if you have any problem. Okay, that's a good catch. Hey, Jack. Yeah, thank you. Okay, that should be okay. Is everyone done with it? I will just wait for 1 minute, just in case anyone is left. And the last term in our Hamiltonian. So if I go up here, so we have already completed the matter Hamiltonian term, the cavity Hamiltonian term, and the diamagnetic term. So in order to get this Hamiltonian P dot A, the last term left is the interaction term, and that's what we are going to compute now. So this is the equation for our interaction term. So we need A dagger A, B dagger B, fundamental frequency, vector potential, our reduced mass and effective charge. So we'll define the function as compute interaction matrix P dot A, and the input parameters will be matter dimension, cavity dimension, reduced mass, our force constant, effective charge, and vector potential, which is defined as A naught. So for this one, we will simply call, first we call the matter ladder operator, and we will store them as A underscore dagger. A is equals to, and we'll again need this function. Yeah, here. And for matter, we'll give the matter dimension, which is matter dim. Now, in this next line of code, we will compute the cavity ladder operators, and we'll store them as B dagger and B. So we have underscore dagger and B. We'll simply again call this function, and we'll give the dimension of our cavity. In this line of code, because we need the subtraction of A dagger and A, we will do that, and we'll store that as A underscore diff, which is equals to A underscore dagger minus A. Similarly, we need the summation of B dagger and B, and we'll store that as B underscore sum is equals to B dag. Actually, we have stored it as dagger, so that's B dagger plus B. Now we need the frequency. We'll calculate and saved at it as omega underscore f is equals to np dot root and k divided by mu. Now we will try to compute this prefactor first, and then we'll simply do the dot product. So the prefactor will save as fac, and we have minus 1 j is equals to yeah, effective charge. So that would be C underscore charge into, what else do we have? And that will be divided by, not into, equals to mu into, we have square root of mu and p dot root. So we have mu into h bar and the frequency which we just calculated, omega underscore f. And this whole term is divided by 2. Divided by 2, and it is multiplied with vector potential, and I think this is our prefactor. Yeah. Now we simply need to put all these terms in the above equation, and we will get the interaction term of the Hamiltonian. Basically, P dot A Hamiltonian will store it Hamiltonian. So first we'll multiply it with the prefactor, and then we will use the Kronecker function of numpy to do the tensor product, which is shown simply multiply these matrices. So basically the the subtraction of A dagger A and addition of B dagger B. And that we have stored as A underscore diff, B underscore sum. And I think it should run. Yeah. Any questions? Oh, I'm not sure where to check the chats, Jay. Previously, I just stopped sharing my screen, so I was able to see that.
Yeah, Bill, just one comment from the chat. Just about Z charge is missing an R, which good catch. Thank you. Nothing indicates people are needing more time. If you do need more time, put up a red X, please. And if everything is good to move on, if you could put up a green check, that would help us. And the react button. Yeah, this looks good to me.
Okay.
Oh, except for the chart, you still need the R in charge.
Oh, okay. Yeah. Good catch. Yeah.
Cool.
And now I would like to hand over to Peyton. So I will
All
just.
right. Excellent work, Ruby.
Peyton, you can share your screen.
Is it sharing?
Yes.
Okay, awesome. Okay, so Ruby just computed the interaction term for the P dot A Hamiltonian, and I will be computing the interaction term for the Pauli-Fierz Hamiltonian here. So we're going to need the A dagger plus A term and the B dagger plus B term, and then we're going to be collecting all of the constant out front into a prefactor term. So first, we're going to need to calculate omega f, the fundamental frequency for the matter subsystem. And then I'll be computing the E naught, the electric field magnitude from the vector potential magnitude. And that is the square root of 2 times the cavity frequency, and then multiplied by A naught. And then we'll compute the prefactor and store it in FAC. The effective charge divided by 2 times square root of the cavity frequency.
Peyton, can you zoom your screen a little bit? It's too small font.
Yes. Is that better? Did that change anything?
It looks good to me.
Okay.
Yeah. Thank you.
Okay.
I'm using a big screen though, so I can't speak. Actually, it looks good on my laptop too.
Okay. So now we have the prefactor computed, and then we will build the raising and lowering operators for the matter subsystem. So A dagger and A. Then it was the matter dimension. Okay. And then we will do the same thing for the raising and lowering operators for the cavity subsystem. And then we need to compute the sum of A dagger plus A and sum of B dagger plus B. So we'll store that in A sum equals A dagger plus A, and B sum equals B dagger plus B. And then we will be taking the tensor product of these and then multiplying them by the prefactor. So our interaction Hamiltonian is going to be the prefactor times the tensor product of the matter subsystem and the cavity subsystem. Okay. Does anyone have any questions? Okay.
You just pause on that for one more minute.
Okay.
Okay. Thank you.
Okay. And then we can move on to calculate the dipole self-energy term for the Pauli-Fierz Hamiltonian. And this only includes the matter operators, A dagger and A. So first, we're going to compute the cavity fundamental frequency again, which is just the square root of k over mu. And then we're going to compute E naught again from A naught, and that is going to be square root of 2 times the cavity frequency times A naught. All right, and then we will compute our prefactor and store it in fac once again, and that is going to be z charge squared times h bar over 4 times mu times omega matter multiplied by E naught squared. Okay. And then once again, we will build the ladder operators for the matter subsystem, A dagger and A. And we will compute the sum of those again. And then for this term, we need A dagger plus A squared. So when we go to compute the dipole self-energy matrix, we will square that A sum and the add symbol just does matrix multiplication. Okay. Missing a parenthesis. Oh, that was supposed to be a 0. Okay. I'm going to just pause here for just a second, make sure everyone is caught up.
Yeah, if you are all good, if you don't mind using your green check, and if you need more time or are stuck, you can use your red X.
Okay, I'm going to zoom out just a little bit so that all the code is visible.
Okay.
Okay, should we move on to the next part?
Yes, let's move on. Okay,
Okay.
great.
Okay, there's no more code to fill in, but next part is using the functions we created above to build the entire, both the P.A's and the Pauli-Fierz Hamiltonians. Jay, do you want to go through this code?
Yeah, I'd be happy to do that.
Okay.
Yeah. Just replace and share. Yeah. Hopefully I've managed to follow along. Okay. And not introduce any typos. Yeah, so okay, so we've set up these functions, and so in principle, what we should have is a function that computes, let me get back all the way to the top here. A function that computes, looks like we've done a lot. The matter Hamiltonian, and the matter Hamiltonian is identical for the P.A and the Pauli-Fierz Hamiltonian. So we just need one function that computes that. The cavity Hamiltonian, that's identical for P.A and Pauli-Fierz. So only one function for that. We need a function that creates the diamagnetic Hamiltonian for the P.A. We need a function that computes the dipole self-energy for the Pauli-Fierz. And we need a function that computes the interaction for the P.A and a different one that computes the interaction for the Pauli-Fierz. So those are the different functions that we've just written. And so what we'll do is we'll call the lines that come after, and they're going to just kind of one by one build each of these terms. And when necessary, they're also going to build identities to take the tensor product into. And you'll notice, hopefully, at least you'll notice that we've done this correctly, that we've got all of our matter, and anytime we take a Kronecker product, we've got the matter Hamiltonian on the left and the matter subspace on the left and the photon or cavity subspace on the right. And that would just correspond to like ordering our basis so that the tensor product basis, the matter states are on the left and the cavity states are on the right. So let's go see what happens. And I'll also walk you through the lines here because, because we're basically done. Okay, so this is where you can define the number of states in the cavity subsystem and the matter subsystem. And so now the overall composite subsystem is going to have a dimension that goes as the product of these number of states. So if we've got 2 photonic states and 2 matter states, then I'm going to have overall 4 composite states, and then my Hamiltonians will be 4 by 4. So let's just start there. Let's actually just run this cell and sort of see what comes out. Oh no, matter Hamiltonian is not defined. So that's good. Let me figure out where I went wrong. I probably didn't run this cell up here. Matter Hamiltonian is not defined.
Yeah, I'm getting the same error. So I think what I have done is instead of taking the capital H, I have taken the small h. So I think you need when I'm defining the matter Hamiltonian in 25th cell, I think.
Yes. What are we printing here? Oh, yeah. Yep. Okay. I see exactly what you're saying. So let's come up to compute matter energy matrix. Yeah. Matter underscore Hamiltonian. So we get 2 fixes here. Either make this uppercase Hamiltonian, so matter underscore Hamiltonian, return matter Hamiltonian. Okay. So let me rerun this cell. And now I'll come back down to the cell where we're printing and try again. And we've got Z is not defined. That's cool. So let's come in. So this FAC is minus Z. Probably this should be minus Z underscore charge. So compute interaction matrix Pauli-Fierz. Yeah, so I might have introduced that typo. Yeah, let's see. Yeah, minus Z charge. Okay, great. All right, awesome. And these are the eigenvalues we're getting. Let's see what's happening. So now the good news here is that we have exactly the same eigenvalues from the Pauli-Fierz Hamiltonian as we do from the P.A. Now the bad news is we have these expected eigenvalues in here, and those are different than what we expect. And so then the question is, did we make a mistake or is there a good reason why they're different? So I'm gonna imagine that there's a good reason why they're different. But if we discover otherwise, we can let everybody know. Okay, so so now let me also explain something right now. So what do we do here, right? We built each of these submatrices, in what I would call a minimal basis, so just 2 photon states, 2 matter states. And so right here, right, we're building the matter Hamiltonian. Here we're taking the tensor product between the matter Hamiltonian and an identity on the photon subspace. So this is the identity on the photon subspace. Next, we're going to compute the cavity Hamiltonian and take the tensor product of an identity on the matter subspace with the cavity Hamiltonian. Then we'll compute the diamagnetic Hamiltonian. That's all in the photon subspace. We want to take the tensor product, the matter identity with the diamagnetic Hamiltonian, and then compute the interaction Hamiltonian for the P dot A. And this will now be in both the matter and photon subspace this term. So no tensor products for this. So then we'll build the full P dot A Hamiltonian in this tensor product basis. It's going to be that matter Hamiltonian tensored into an identity for the cavity, identity for the matter tensored into the Hamiltonian for the cavity, diamagnetic term, which is an identity for the matter tensored into diamagnetic for the photon, and then the interaction. And then we'll do the same thing for the Pauli-Fierz. The Pauli-Fierz has got a different interaction matrix than the P dot A, so we compute it here. The dipole self-energy is also unique, so we'll compute that here. The interaction for the Pauli-Fierz is actually already in a tensor product basis, but this is just in a matter-only basis. So we need to take a tensor product between the Pauli-Fierz Hamiltonian and the identity and the photon subspace, and then build the full Pauli-Fierz Hamiltonian in this tensor product basis as the sum of all of those terms. And then we'll diagonalize each of them. And something very peculiar about the harmonic oscillator, if the matter subsystem is the harmonic oscillator, then in fact, you should always get exact agreement between the eigenvalues of the Pauli-Fierz and the P dot A Hamiltonian. So when we see this result down here where we get exactly the same eigenvalues out of both of these Hamiltonians, that's a good sign that we have implemented these consistently. And I mean, they're exactly the same, element by element. The ground state here exactly matches the ground state of the P dot A. First excited state of Pauli-Fierz exactly matches the first excited state of P dot A, and so on. As soon as you don't have a harmonic oscillator, so let's assume that for the matter Hamiltonian, you introduced some anharmonicity. Maybe you had a quartic oscillator, or maybe you had a Morse oscillator. As soon as you do that, actually, you will not, in general, find that the eigenvalues of the P dot A match the Pauli-Fierz Hamiltonian. They have to be the same in the exact limit, but that essentially means going to a complete basis limit. And so for a truncated basis, you can see disagreement in the eigenvalues. But the harmonic oscillator, that is not the case. And that's kind of cool. All right. So now let's also come down here and let's run this cell. So now what we're going to do is we're going to actually look at the new states that have formed from the Pauli-Fierz Hamiltonian. And so we have, in this case, looks like the ground state has kind of been shifted up a lot too. I wonder if what has happened is if our coupling is quite strong. So I wonder if that's actually what the issue is. So let me come over to so it could be that we kind of broke this example by using really strong coupling. Is that what happened? No. So this is what we're expecting things to look like. I guess the only other thing I'm wondering, I bet what we have done, I bet what we have done is we have included the 0-point energy in both the matter and the photon. And that's probably not something we did in the notebook. I'm just going back in the original notebook.
Yes, Chair, we have included.
Yes. And is that why we are offset?
Yeah, that might be one reason.
I think that's why we're offset. So there's the cavity. Well, it appears that we intended to have. Let's go back and look at those 0-point energies. I think there might be something still wrong with our 0-point energies. Okay, matter Hamiltonian 1/2 I. What happens if we just get rid of the cavity 0-point energy? True. Okay. Now we're matching the expected values. And now if I plot this, now it's going to look right. Okay, good. Okay. So that was the thing. And so we had this remark yesterday about sometimes it's convenient to omit the 0-point energy of the cavity. So I think in our example, we wanted to omit the 0-point energy of the cavity. And so the expected output was neglecting the 0-point energy. And now this plot looks a lot nicer now that we've neglected the 0-point energy. Okay, so these red dashed lines that we have plotted, these are the energy eigenvalues of just the HF system. So the vibrational ground state is in red dashed lines. Vibrational first excited state is in red dashed lines. Second excited state in red dashed lines. Now what we've plotted in these purple dashed lines, these are the energy eigenstates of the coupled Hamiltonian. Okay, so we have the ground state, and you'll notice that actually the ground state is not exactly equal to the ground state of the uncoupled system. And so this is something that you'll get out of these rigorous Hamiltonians that we've shown you, the P dot A and the Pauli-Fierz, is you'll actually see modification to the ground state under strong coupling. There are models which are really commonly used in this field, like the Jaynes-Cumming model or the Rabi Hamiltonian. And those are models which will not modify the ground state. You will not see any ground state modification through those models. So you really need to go to some model like the Pauli-Fierz or the P dot A Hamiltonian that's got these diamagnetic terms or the dipole self-energy terms to actually capture this modification to the ground state. Okay, and then these states here, this purple state below the first excited state and the purple line above the first excited state, these would be the polariton states. And so you can see this, roughly symmetric splitting above and below the original excited state of the system, and that you will capture with these, Jaynes-Cumming type Hamiltonian. So anyway, yeah, and you can now, the other thing I guess it's probably worth mentioning, because we are well within our time, is that now if you were going to do spectroscopy on this system in a cavity, right, one of the features that you would see is that without coupling, so outside the cavity, right, your HF molecule is going to have this fundamental transition from this red line to this red line, right? And there's some energy H bar omega associated with that. and some wave number associated with that you would measure spectroscopically. So now I stick this thing in a cavity and I do spectroscopy, and I have different transitions, right? I would have basically this lower purple line, which is about at the ground state, up to this purple line, which has less energy than the original transition. So I'd see a red-shifted peak, but I would also have a transition from this, new ground state from this purple line up to this upper polariton state, which is going to be blue shifted in energy. So a sort of spectroscopic feature of strong coupling that you see is a splitting and some absorption feature into two peaks. And this is sort of the underlying reason here. I guess the only other thing I would say is that if you want to see each of the matrices, you can run this block and you can just sort of see the structure of each matrix, right? So the bare matter Hamiltonian in the basis of matter energy eigenstates is a diagonal matrix. If I take the tensor product of that matter Hamiltonian with the identity on the photon subspace, I basically get a sort of embiggened version of that diagonal matrix. This is the bare photon Hamiltonian, also diagonal. This is it in the tensor product basis. And the diamagnetic Hamiltonian itself is diagonal. And the interaction matrices are off-diagonal matrices. And if you come down to the dipole self-energy, in general, this can be can have both diagonal and non-diagonal contributions, but there's, I guess, something about our system, our model system, which is relatively simple and makes it diagonal. But if you were to do, look at the dipole self-energy for, our molecules under electronic strong coupling, you'll typically see that those dipole self-energy matrices are off diagonal as well. So yeah, I think that's it. You can read a little bit more about these extensions to anharmonic oscillators. There's an example that you could follow for the Morse oscillator here. And we have some on electronic strong coupling here. So yeah, plenty more to do if you want to keep experimenting with that. But yeah, I guess that's about it that we have prepared. So we'll just open it up for any questions or comments. And I do also have a survey that I'd really appreciated if you would complete. So we'll also link to that. Yeah, Arthur, go ahead. Yes, yeah, absolutely. Yeah, let me go back to screen share. So basically the error the error that I corrected, it's not necessarily an error, it's just a sort of a choice. When we computed this expected output, we were choosing to neglect the 0-point energy of the cavity. And then when we implemented this today, we included the 0-point energy of the cavity. So the 0-point energy of the cavity is coming basically from the 1/2 times the identity matrix in the Hamiltonian matrix builder that we wrote. So if you want to exclude the 0-point energy, you can remove that identity term, or you can just multiply it by 0, which is what I did. So I just changed the 1/2 times the identity to 0 times the identity. And then I just stored that, reran that function and then reran the part which builds all the Hamiltonians and diagonalizes them. And the syntax error which happened. I'm not sure. There was a couple of syntax errors. One of them, I don't know if I'll remember all of them, but I think in the Pauli-Fierz interaction Hamiltonian, my function had a z instead of a z underscore charge. And there was one other syntax error. I think it was in the matter Hamiltonian. There was a capitalization mistake. So let's go back to the matter Hamiltonian. Compute matter energy matrix. Yes. The capitalization of the assignment of the matter Hamiltonian needs to match the return capitalization. So I think we had matter underscore lowercase Hamiltonian in the assignment, but matter underscore uppercase Hamiltonian in the return statement. So you can swap either, just so long as they match. Cool. Yes, more questions, Arthur. Go ahead.
Sorry, can you hear me now?
Yes.
Thanks. I just would like to thank you all. It was really good, really nice, this workshop. And great reference. The material was awesome. And
Awesome.
maybe, is it possible to provide a certificate that we attended this workshop?
Oh, that's a great idea. You know what? I would be happy to. So I want to make sure that I had not thought about doing this. I don't have any problem with doing this per se. I want to make sure. So we sort of did this on our group did this on our own. I want to just make sure that by issuing a certificate, it's not somehow indicating anything on behalf of our institution, on behalf of UNC Charlotte, who did not have any oversight. So I will get back to you on that matter, okay? And I can't promise we can do it. I don't have a problem with it, but I need to make sure that it's not somehow going to imply some kind of action on behalf of UNC Charlotte. Does that make sense?
Of course, no problem. Thank you once again.
Yeah, absolutely. But I'm glad that it was helpful nonetheless. Okay, any other questions? All right. Oh, Daniel, any questions from your group?
Any questions for the group? What was the reference for the paper that you were looking at? Can you hear that, Jay?
Say one more time.
The reference for the paper that we were looking at was like the digital prime. He sent a document. Okay. Yeah, I can send that to you later. It was about the primer that you sent earlier.
Oh, yes. Yeah, exactly. Yeah.
Yeah, no questions. Any more questions here?
No, it was great.
Yeah, no questions here, Jay. That was awesome. That was really great.
It was fun.
Yeah.
Great.
I got to the wrong results and I was wondering if that was really intentional or not. Yeah, turns out it was intentional. So good.
It was yes. I guess we'll pretend it was intentional.
Yes. just a convention.
Yeah. I would encourage you to go back and increase the basis too. So if you increase the size of the basis, then you'll actually break that agreement. So that agreement happens with a minimal basis, but you'll improve your results with more photon states and matter states, and then it'll break the agreement because the minimal basis is not everything.
Yeah, we'll totally try that.
Or it shouldn't be. Yeah. Cool. Well, again, I urge everybody to please complete the survey. There's a handful of questions just about, you know, if you learned anything useful, number one, if the background material was helpful, if you looked at the background material, that sort of thing. So we don't have any immediate plans to do this again, but you never know. I suspect we will probably do it again at some point. So feedback would be helpful for us.
Awesome, yeah. You really should do something like that again, yeah.
Well, thank you. Should we do exactly the same thing, or should we change it up?
It's up to you. We're going to participate regardless.
Okay, great.
Are you planning on doing anything more like that involves more electronic structure?
Yeah, we could do that too. That was originally how I was thinking about doing it, but then I think the idea of doing a model system, which is a little bit more manageable, seemed more attractive. Yeah. But we could do, you know, I think we're pretty much ready. We have the material that we could do the Hartree-Fock theory on Pauli-Fierz Hamiltonian. So that's we could do that.
Yeah,
too.
but that was really useful for beginners, right? People entering the field. That was great.
Yeah. Cool. All right. Well, today was a little bit more concise, I guess. I was I watched a little bit of how yesterday went, and I think I don't mean this to be a knock on David Sherrill at all, but I think I beat him in terms of slowness of pace in an online lecture. Because if you go and watch some of David Sherrill's videos, you can't imagine how someone could possibly be more slow and, you know, paced in their lecture, but I think I'm actually even more so.
Well, I enjoyed it.
Okay, good. I shouldn't have said that while I'm recording. Oh man. All right, well, let me hit stop recording in case I